Okay, it is 6:30, so let's go ahead and get started. I want to first of all thank everybody for being here at 6:30 in the evening. So we greatly appreciate that. We know it's late and you have other things that you could be doing. So today we're going to be talking about debugging performance issues using Visual Studio 2015. My name is Andrew Hall. I'm program manager on the diagnostics team. We own the debugger, the profiler, IntelliTrace, and the new Android emulator that you may have seen in the keynote if you're into Android development. I have been at Microsoft for about 7 years almost. I wrote line of business apps for a little bit after college, went back, got my master's degree, and then had the opportunity to go join the Visual Studio debugger team, which is where I went, and I've stayed on that core team my whole time at Microsoft because I love developer tools.
Hi everyone, my name is Angelos Petropoulos, and I'm also a program manager for Visual Studio. I'm originally from Greece. I moved to the UK for a few years, and a little while ago I came to the US, and I joined Microsoft in Visual Studio Diagnostics, same team as Andrew.
So, excellent. So first thing, submit an evaluation after the talk. We know that everybody's going to love this talk, so you're going to rate it very highly, but it was supposed to be funny. Let's talk about performance. So let's get started really quickly. Man, don't you hate it when that happens, Angelos?
I thought you fixed that.
I blame the PowerPoint team. So briefly, why is performance important? I think everybody here, probably you're here because you care about performance, but we know that as a user, it's incredibly frustrating when you wait. It's one of those things that we tend to not think about a lot while we're developing until we actually have a problem. Happens to us in Visual Studio, just like I'm sure it happens to you. You ship it, customers go, oh gosh, this is so terrible. And you go, oh yeah, how did we miss that? So it's important to think about performance. And actually, a study came out a little while ago, and they determined that in app stores, performance is the number 3 reason that applications get bad reviews. Behind it simply freezes or it crashes, right? Pri 0 is it has to work. Pri 1 is it should actually work fast enough that it's usable. And so yeah. So with that, let's talk about what we're going to talk about today. First thing we're going to talk about are new tools that we've integrated into the debugger. As I mentioned, we want to move the idea of performance testing upstream. So all of us who are developers spend time writing code, you debug your code. We brought some performance tools into that debugger workflow. So just as you're running code, you can monitor your performance. Things might jump out at you that might have otherwise escaped to much further in production. And then we're going to talk about how do you drill in and use tools that run outside the context of the debugger, because obviously there's limitations to what we can do under the debugger, and this is a new direction we're taking, so we have a richer suite of tools that work outside of the debugger. And we're going to talk about 3 tools there. So with that, I'm going to turn it over to Angelos to demo.
All right. So for the first demo, what we're going to work with is a relatively simple WPF application. I'm just going to hit the start button to fire it up. And you see it's taking a little while. Fairly simple. It's a list of pictures from a specific directory. I can double-click to open one of them. And the first issue, the first performance-related issue I want to address is it took a little while to start up. And I've actually seen it in some other environments. It takes a bit longer. I want to figure out what's going on. So the first thing I'm going to do is I'm going to find the setup, the initialization of my application. I'm going to set a breakpoint at the very first line of code. And I'm just going to restart debugging. We have a handy little button here that will do that for us. So before I drill into how I'm going to fix this problem, I want to take a minute to show you something. So no code has been executed yet, and I'm just going to press F10 to step over this line of code. So I hope that most of you noticed that right next to the current instruction pointer, I have a little tip, what we call a perf tip, which is telling me how much did the last line of code took to execute. Now, it might be a little bit confusing. Why am I showing this number next to the line of code that hasn't executed yet? But hopefully, that will make sense when I show you this. If I put a breakpoint at the end of the method, line 65, and I press F5 so that it will execute lines 62, 63, and 64, you'll see that it actually gave me the cumulative value for all of the lines of code that were executed until it hit the breakpoint. So basically, I'm in complete control here. I can either step over just one line of code, I can run to cursor or use a breakpoint and execute 5 different methods. It's up to me to decide what granularity I want. So this perf tip is telling me that it takes about a second to start up my application. And just by reading at the code, I see that I have line 60 that initializes a new list, line 62 that retrieves the files from a predefined location, line 63 that removes file types that the application considers incompatible, and then finally the pictures are loaded into memory and into the list.
Now, I have a quick question before you move on. We know that we're running under debugger. Debugger can do all sorts of weird things, like has to stop and load symbols.
That's right.
For example, so this perf tip, you're stopped for a while. Is it counting time that you're stopped in the debugger? Is it counting time that we're spending like loading symbols?
That's a good question. So what is this number telling me exactly? What it's telling me is that this is the time it took to run the application. So no matter how much time I spend on a breakpoint or while I'm stepping, it is irrelevant. The other thing to notice is, yes, we're currently debugging, and at the same time, we're kind of measuring performance. And some people might say, well, what about all the overhead that just debugging adds? Well, the answer is we've gone to great lengths to make sure that we remove any overhead that we can detect that is because of the debugging. Now, of course, we cannot be perfect. We cannot be absolutely certain that we removed every little bit of overhead. So if you pay close attention to the number, it actually says that the elapsed time is less than or equal. So what we're telling you is there's no way this took longer. But there is a chance that if you run this with release mode in production, it might actually be faster. So the way you're meant to use this information is if you're running through some code and the value seems OK, whether it's 5 milliseconds or 7, that's fine. Ignore it and keep going. But if you step over some code or execute a method that catches you by surprise and it takes 2 seconds and you didn't expect that, that's just a very early on hint to tell you, hey, before you keep writing code the way you're writing it, you may want to check on this potential performance issue because this method call took longer than you thought. Answer the question?
Yeah, thank you.
Cool. So what I'm interested in now is figuring out which part of my startup path is taking so much time so I can figure out where to focus. So what I'm going to do is I'm just going to move my current instruction pointer to the beginning of the method by dragging it. Click and drag. And I'm going to step over each one of these lines of code so I can get an idea of who is mostly at fault here for the slow startup. So I'm going to F10. That only took 1 millisecond. I'm not worried about it that much. F10 again. Getting all the files took less than 5 milliseconds. Again, orders of magnitude, a second to 5 milliseconds. I don't think I can do much there. F10 once more. Well, that's surprising. Removing invalid file types took about 700 milliseconds, which is almost the vast majority of the startup time. And the very last part, which is actually loading the images, took only about 200 milliseconds. So this is not what I expected. I was actually expecting the loading part to take longer. So let me just do this one more time, because why not? We always want to try to make sure that we didn't hit a glitch, right? Maybe the disk was being used by something else. It's always nice to just double check your numbers. So I'm just going to do this one more time, just to be sure. OK, that seems fine. That seems fine. Again, most of the time is being spent here, and loading files takes about the same amount of time. So I'm pretty convinced that the first place I should look here is what remove invalid files does. So I'm just going to select it and hit F12 to go to definition. And I can see here that we are being passed an array of files. We're going through each one of them using a utility method to validate whether the file is valid. And if it is, it's added to a list that is eventually returned to me. So over here on the right, you may have noticed that there is a new diagnostics tools window. And one of the graphs that you have there is a CPU utilization graph. And just looking at it, I can see that I have plenty of CPU power left. So if I just let my mouse there sit for a little bit, it tells me that one of the highest peaks was about 20% of the processor. So I think I have some room here to do some parallelization and improve the performance that way. I actually have already, of course, for the sake of the demo, written another method that says remove invalid file types in parallel. This takes exactly the same argument. It's using a concurrent bag instead of a list because I'm going to use a parallel for it, and I need a collection type that is thread safe. And it's just doing a parallel for each, again, using the same utility method, adding the files to the valid list of files and returning it. So I'm just going to go back to where my startup path was, I'm going to use edit and continue to just use the new method that I found. And I don't know if some of you noticed this new feature in 2015, this little light bulb came up right next to my edit. I just want to briefly give a shout out to this cool utility, which lets me actually, if I was renaming the method rather than reusing another one, it will allow me to do some cool refactoring from here. You could just go and rename wherever this method is being called from. So I'm just going to do what I did before, move the instruction pointer back to the top of the method. And now I'm going to try and see if doing things in parallel has improved performance overall. So I'm just going to press F5 and hit the very end. 800 milliseconds versus 1 second. It's slightly improved, but let's see exactly what's going on. I'm going to move back to the top, F10 through all of them. Everything else is fine. Let's see how long this one takes now that is in parallel. This is taking about 650 milliseconds now. It's an improvement, and I can actually see in my CPU graph that I am actually making use of the CPU. So I have made things better by making them parallel. But I'm still not happy that the fact that my finding invalid file types is taking longer than actually loading the images. I don't think that's acceptable. So I think at this point what I want to do is drill into the functionality of finding invalid file types. So I'm just going to press F12 to go to definition again. And since the only thing that this method really does is use the utility method is valid image file, I'm going to take a look at that. Again, I just pressed F12, and it takes me to the definition. I'm just going to take a look at this method. It looks like what it's doing is it's actually loading the file, grabbing some bytes, and then the idea behind here is that we can check the first few bytes of various image types and confirm that they really are the type they're saying they are. So for example, it looks here like for JPEG, we have to check the first 11 bytes. Then for PNGs, 8 bytes, and so forth and so on. But if I take a look up here, it looks like I am actually loading the entire file, even though I'm only using only the first 11 bytes at most. So maybe one of the optimizations I can do is only load 11, which is the worst case scenario. And then that should make it better because I will be loading less stuff from a disk.
Hey, Angelos?
What's up?
You're dev, aren't you?
Yeah.
Let's think about this from a customer perspective.
What's up?
Maybe we could just look at the file extension.
OK.
I mean, if somebody misnames their file, they take a file that's not really a picture and calls it a JPEG, let's just won't fix the bug.
OK, where was this idea when you wrote this code?
Hey.
OK.
I've thought better of it since then.
OK, all right. So I kind of agree with that. I mean, this is on my local hard disk, and it's taking so long. What if the files are on an external hard disk or a share? It's even going to take even longer. So I agree with that. That makes total sense to me. So what I'm going to do is I'm going to go back to my remove invalid file types in parallel method. And for the sake of a demo, I've already written a different method that will find invalid image files based on their extension. So let's go back up at the startup path of the application. Same old story as before. I'm going to move the current instruction pointer to the top. And now I'm going to go and F5 and see if that made it any better. Well, that's a lot better now. It's at 185 milliseconds. Now let's see how that relates in between removing the file types and actually loading the files. So I'm going to step through the first part. Not very interesting. This is where I'm really interested in. I see that took less than a millisecond. I think that doesn't get much better than that. And then finally, most of the cost, if not all of it, is from actually loading the files. So I think at this point, I'm pretty happy with the startup. So what I'm going to do is get rid of these breakpoints and just continue the application. All right. Going back to the slides. So what I briefly showed you here is a brand new feature in 2015 called perf tips, and how I was able to continuously make changes and test my theories and my hypotheses very quickly while I'm debugging. Something that you couldn't really do before, because typically running the profiling tools has some overhead. You have to make your changes, compile them, run them, stop it, take a look at it. I'm usually not so keen on making very off-the-cuff hypotheses when I'm running the profiler, but here you saw how very easily I took a guess about parallelization. It didn't work out very well. I kept digging deeper, fixed the bug, now I'm done. And you also saw how the CPU graph is a great companion when you're just debugging. Because, OK, it's not the most amazing feature. It doesn't give you the most amazing information. But it gives you an idea of what's happening to your application and how it's behaving. So when you see that something is taking a long time and your application is not using the CPU, then that's how you know, hey, maybe I can spin up some more threads. And I can get better performance out of this. Any questions so far? So the question is, do perf tips work with remote attacks? And the answer is yes. They work pretty much anywhere you can debug. That's native code, managed code, remote debugging in Azure. Wherever you can debug, you can pretty much get perf tips.
Yeah, so the question was the time will be based on the remote instance. Yeah, so basically the debugger right before we say resume the process and we get the notification that the process has been stopped either from a breakpoint or a step complete, that's where we do it. So yeah, if you're remote debugging on Azure, all of the measurements occurring in the remote debugger that's talking to that process exactly. So you're not going to pay any latency cost there.
Yes?
Can you see the perf tips for the previous lines of code that were run? So like you had 10 lines of code in that function, and at the end you want to see what every single one without having to step through them?
Can you just, so the question was, can I see the history of the perf tips? Because as you saw, every time I step or hit a breakpoint, the previous one disappears and the next one appears. I'm going to ask you to take a look at the bottom right corner of the screen right now. And as you can see there, you can see that for every step I've taken and every breakpoint I've hit, I have an event in my list within diagnostics tools. And one of the columns is duration. So that's the history of your perf tips. You can see every step you've made and every breakpoint you've hit, and it keeps a track of the perf tip at that moment in time. Yes, please. The question is, can you make use of these features while you're unit testing? And the answer is yes.
When debugging your unit tests. I said when debugging your unit tests. It doesn't, obviously the debugger's doing all the measurements, so. So this is specifically tied, so the question was, what about load testing or something like that? So this is specifically the debugger measuring how long the code runs from point A to point B. We'll talk a little bit later about tools available for measuring performance of processes outside the debugger that capture a view of the entire process and everything going on. One more question here. So the question is, what level of licensing? This is available down through the community edition in Visual Studio 2015.
Yay. Go ahead.
So the question was, will edit continue work over remote debugging? As of Visual Studio 2015 RC, yes, it does.
Yay.
And so there's a blog post. Our blog address is at the end of this. There's actually an environment variable that you can set in a process before you create it that will now also enable edit and continue on attach as well.
There were a couple of questions over here. Yes. So the question is, can I, whatever data I've gathered within the diagnostics tools window, can I export that and save it? The short answer is, for right now, no, but we're definitely working to make that happen. All right, any more questions? There's one more there.
We are not doing, so the question was, what about happening on the graphics side? There's no GPU integration here, so we're not going to show you any of the costs spent drawing on the GPU. Is that your question? Yeah, no GPU integration with this tool. We're using Query Performance Counter. So the question was, which performance counter are we using? Yeah, so we should probably move on.
I feel like there was one question over there that I ignored, and I hope I haven't annoyed anyone. OK, great. OK, so I'm going to keep going. And next, we're going to look at, well, yes?
So the question was CPU usage and memory usage. We'll get to that.
Yeah, give me a sec.
Promise. Great question. Thank you.
So before we move on, just a quick recap that we saw. First, we saw perf tips. which is a very quick and easy way to measure how much time has been elapsed between two breaks, whether they're breakpoints or steps. We've talked about how most of the overhead that is related to debugging has already been removed from the number. But at the same time, just to be aware, we're constantly trying to improve that. And we make asks to the CLR, we make asks to Windows. So as the CLR and Windows rev up, we're going to get better at it. So right now, our best accuracy is CLR 4.6 and Windows 10. And it will just keep getting better. And we also quickly saw the CPU graph, which, as we talked about, shows me utilizations across all of my cores. So keep in mind, if you only get 25% of CPU usage, that probably means that one of your cores is working at 100%. We saw how spikes and valleys can be interesting, because they can tell us whether there's any room for parallelization or not. And the graph is there after you stop debugging, so you can still keep a track of what happened even if you stop debugging. So next, let's jump into another demo. Same application as before. What you haven't seen yet is that I can double-click on a picture, and I can take a look at it and close it, double-click on another one. And what worries me is that every time I do it, if you keep your eye on the memory graph here, you'll see that it keeps going up. And I'm not really very happy. Oops. So it keeps going up, and I'm not really happy with the fact that just looking at pictures, it actually does that, right? So what I'm going to take a look at is why would opening pictures and closing them actually cause this issue. So what I'm going to go do is find the event handler for me double-clicking on the list, which is right here. So these two lines of code. It looks fairly simple to me. It just has a new type called image page that loads up, and it's just shown. So I'm going to put a breakpoint just before this line of code gets executed. I'm going to go back to my application and invoke the functionality. You can see here how my memory graph was going up just as I was trying to do that. So right now, just before I've actually invoked the double-click code, I'm going to use the memory usage tab. And what I'm going to do is I'm going to make use of a functionality called take snapshot. Now, what this just did is it actually went through my process, and it looked at how many objects I have alive and how much space they're taking up on the heap. Now, one thing to keep in mind is the number that you see up here in the graph, the 130 megabytes, might not match what you see here in the heap size. And that's because the graph is showing you private bytes. That's pretty much everything except for the actual assemblies, the actual modules. What the memory usage tool does, and the snapshot functionality, is it only gives you what is on the managed heap. So even though we might write some managed code to load an image, if we're using a type like bitmap image, that type actually has a native representation. So the managed heap just has a reference to it. So that size is not going to be taken into account here. But that doesn't mean that this is not useful, because take a look at this. What I'm going to do now is I'm just going to step through a couple of lines, which basically invoked my code for the double click, and I'm going to take another snapshot. Now, immediately, what the tool will do for me is it will compare the snapshots. And if I keep taking snapshots, it's going to keep comparing them. And immediately it tells me that there were about 500 new objects and about 5 more megs on the managed heap. Now, what I want to find out is, why does my memory keep growing? So what I want to do is figure out what this delta is all about. So I'm going to click on the delta. And this opens up what we call the managed heap. A little tip here, if you want to get full screen view of a particular tab, you can just drag and push it to the top of the screen, and now it's full size. So here, what I'm getting is a table. The left-hand column is showing me every type that my application is using, even though it might not be a type that I created. If my application is making use of it, it will appear here. And next to it, you will see in various different columns, different metrics for these types. So let me take you through each column. The first one says count diff. This is telling me how many new objects have been created between the two snapshots I'm comparing. The next one is total size diff. This is telling me how much this type has increased in size between the two snapshots, but just that type. Its children are not being counted here. The next column talks about inclusive size. So this is the difference in size between the two snapshots of the type, but including its children. So if this type referenced another type that was even bigger, that would be accounted, and these two values wouldn't be the same. Then you just get the row count. This is how many instances of this type do we have right now in this snapshot. And then total size and inclusive size, again, for this very snapshot. So I can see here that I'm creating a new image page. That's expected. That's what my code did. But what's actually worrying me is the count in my current snapshot is 8.
I have a quick question for you, Angelos. I know you were playing with this before the demo.
Right.
I don't see many objects in the heap. I think there's probably a lot more objects in the process. Why do I only see 3 objects in there?
Good question. So by default, we try to make this view as useful to you and as easy to use as possible. So we do some filtering. And let me show you what happens when I undo the filtering. Top right corner over here, if I click on it, I have 2 options, just my code and collapse small object types. First thing I'm going to do is I'm going to untick collapse small object types.
It's actually worth pointing out this one's uncollapsed. This one's off by default. You had actually left that on.
That's correct. So here, what you see now is every single object, no matter what its size is. And as you can see, the list is quite big. I don't know if you can notice the scroll bar, but I can keep going for a long time here. So what this option does, this very useful collapse small object types does, is it looks at the overall usage of the application, and any type that takes less than 0.5% inclusive size is omitted. So if any type here is taking less than 0.5% of the overall memory, it's probably not your problem. So we're trying to remove that from the view, then you can focus on the larger objects.
Can you talk about what inclusive size is?
Yes, so inclusive size, as I briefly mentioned before, is actually the difference between size and inclusive size is, let's say you have an object, and you have a whole bunch of properties that are strings and byte arrays, and it takes 2 megabytes. That's its size. But if it also had, let's say, 5 children, that each one of them took 2 megabytes, then the overall size is its own 2 megabytes plus the size of each one of the children. Make sense? So the other option, the other filtering option that I have here is just my code. This is slightly different to the debugger's definition of just my code. This is basically some sort of, think of it like a regex query. Basically, it's trying to eliminate any types that we are pretty certain they're framework types and you're not going to be interested in. That's all. So I'm going to re-enable my filtering, because it's much nicer to only work with 3 rather than 1,000. And now that I have an idea of what's going on here, I'm looking at the count. It's 8. But that's not how my application works. When I open an image, I close it and I open another one. I never left anything open. So I'm not really sure why I have 8 still alive. I was expecting that to be just 1. So what I'm going to do is I'm going to go to the bottom. And I'm going to look at the tab called Paths to Root. Now, this list, this tree view actually, it's telling me for the type that I have selected up here, image page, what are other types holding a reference to it? And why is that important? In .NET, the way that memory management works is you just create new objects, you assign to variables, and then you don't worry about it. You expect that as soon as you cannot access the variable anymore, that .NET is going to clear it up, and you don't have to worry about deallocating the memory. Well, the way that the garbage collector in the CLR works this out is it just looks at who is referencing its type. Its object instance. And if somebody that is currently in scope is actually referencing it, they're both going to stay in scope. So what I'm curious about here is what is holding a reference to image page? Because if we go back to my code, let me just minimize this for a sec. You'll see that I don't have a class scope variable anywhere, right? I just have a local variable. So I'm expecting that as soon as this code finishes executing, that somebody's going to clean up my image page, but clearly that's not happening. So let me go back, select this type, and try and figure out what is holding a reference to this type that is preventing the garbage collector from cleaning it up. I see the first thing is an image page. It's a cycle dependency, so I can ignore that, because if something is referencing itself, as soon as itself goes out of scope, we clean up. So no problems there. Next, well, how many times have I seen this? So an event handler is holding a reference to something. I mean, I don't know about you guys, but I've had many times where I've registered for an event, everything works fine, but I always forget to unregister from the event, and that means that the event actually has a reference to me. So as long as the event is around, I'm not going anywhere. So I'm going to go back to my code and take a look for selection.
Actually, Angelos, before you leave this view real quick,
yeah.
I noticed a little icon popping up here when you were hovering over. Can you tell me about that?
So the table here, it's showing you object types, right? It's classes, not actual instances. But what if you want to know these objects are still alive? What are they? I want to inspect their properties and figure out something more about them. What I can do is I can select the type and click on this little icon. And what I will do is it will actually take me to every instance that is currently alive on the heap. And it will show it to me in this tabular view along with its size and inclusive size. And because this is just an object on the heap, and because we are stopped at a breakpoint right now, I can actually make use of the debugger to inspect this object, just like I would within my code editor. So I can just use data types here, and I can inspect the properties just like normal.
Cool. So Angelos, going back, I'll mention, this was added in response when we were building these tools. We worked with the Visual Studio Online team, and they told us they really needed this capability, because a lot of times they'd have 2,000 objects in memory. Like, well, 1,000 of them are something that should be in memory, 1,000 of them aren't. I need a way to figure out which ones are the good ones, which ones are the bad ones. So that's where it comes in useful.
Yeah. So I'm going to go take a look for the event handler now. And because this is a demo, of course, it's right here on closed. I am not unsubscribing from my event. So I'm going to do just that. I'm going to stop debugging. I'm going to uncomment that. I'm going to start debugging again and see if my problem has been indeed fixed. Now, I could just keep an eye on the actual graph, but I always like to test my fix the same way I tested my bug, right? I don't like to take shortcuts because you can miss things. So I'm just going to do exactly the same thing as before, take a snapshot, execute these 2 lines of code, and then take another snapshot.
You actually need to run. It's still on your stack.
Yeah, the count shouldn't have increased, though. So as soon as I fire this up, and I take a look at my view, I can see that the count of image pane is just 1. And I'll keep doing that. Keep doing that a little bit more. A couple of more times. A couple more times. And then I'm going to go back, put the breakpoint, do it again, take a snapshot. I'm going to compare that with last time, make it full screen. And I can already see that my type image page only has a count of 1, even in the most latest snapshot. That was after me opening a whole bunch of pictures. And I can see that my count diff with the very first time I opened the picture is 0. So I've verified my fix. That was indeed the issue. I don't need to worry about this anymore.
So quick question, do you have to be at a breakpoint to take a snapshot?
So the answer is no. You don't have to be at a breakpoint to take a snapshot. I can just show you this right now. Let me just F5. As the application is running, I can hit take snapshot just fine. Everything works as before. The only difference is if you want to take a look at the heap view that we just saw before and you want to go and inspect the instances of the types, you can only do that if you're stopped at the breakpoint, because we have to use the debugger to show you the data types, right? That makes sense. If you're not in break mode, the debugger cannot access the data to show it to you. All right, I'm just going to stop debugging and go back to the slides.
So actually, I have one quick question for you before you move on, Angelos.
Sure.
You talked about the managed heap, and we were only seeing the managed heap. Is there a way I can get access to native data as well?
Is there any way you can get access to native data as well?
Yeah, I'm interested in, I have an application that's C# and C++, and I want to see the native memory as well.
I don't know, can you?
Absolutely.
How?
So
Go ahead.
in this tool, we key off of the debug settings. So if you have a managed only debugger, we default to managed. If you have a native debugger, we default to native. And if you are debugging both managed and native, so I can, for a managed project, if you're starting from C# or Visual Basic, you check this enable native debugging box. And when you start debugging, it's going to now, native memory profiling can be actually very performance intensive in the application. So we're going to make you opt into that. And now I'm going to have to restart debugging. And now, when I take a snapshot, and you'll notice the application may run a little slower in some cases. When I take a snapshot, I have access to both managed and native
allocations.
data. And so the native is going to do tracking of all of my allocations. And so when I click on this, it's going to bring me in. I think we have a few quirks in the way. And so all my objects have been filtered out in this particular case. And just so happens that I'm running against a version of the runtime that didn't have anything interesting, so it's just showing me that it can't determine the types. This memory functionality to get type information requires that you be compiled with the Visual Studio 2015 compiler. So if you're doing C++ development and you want type information for your types, you'll have to build that binary with the 2015 compiler. So, but we do have native memory as well.
All right. So very quickly, we just saw a demo of the memory tool and how you can use the snapshot functionality to find where memory is being licked or memory is being used and not cleaned up. And you saw how you can also use the graph to keep an eye out to your application. I actually noticed this issue just because I was running in debug and I noticed the graph going up. I didn't actually know it was doing that. So just to quickly recap, the memory tool allows you to compare consumption of memory over time. It has cool filtering capability that takes most of the noise out. So I suggest that you always opt in and try to filter the view down before you get frustrated by the thousands of objects that are on your heap. As Andrew just showed you, it works both for C++ and .NET, so it's both managed and native. And I think it's pretty cool, actually. All right. Now over to you.
All right, excellent. So as Angelos mentioned, that concludes the portion of our talk where we are looking at applications or tools that work with the debugger that we have today. Are there any questions on the memory tool before we move on? Okay.
I've used other tools before, and I found that not doing a garbage collect sometimes skews the results.
Oh, great question.
Great
so
question.
The question was, I found that not forcing a garbage collection would skew the results. So when we go walk the heap, we simulate a garbage collection to build that view for you. We know the things that are not referenced, and we do not show them to you in the list. So the memory graph itself will still show the fact that the object has not been collected, but when you look at the counts, you won't see them appear in there, and you won't see them appear in the reference graph either. So, any other questions? Right here.
What about if I have my own allocators for native memory allocations? How do I make them work with this cool type system?
So the question was, if I have my own memory, my own allocators, how do I make them work? The short answer is there will be documentation on how to do that. It's not available yet, but I think by the time we RTM, MSDN will include documentation that tells you how to do that. So is that a sufficient answer for now?
Yeah.
You'll have to do some work to opt your own allocators in to make it support the type information.
Oh, sorry, there's a question right there. Oh, I'm sorry, I've been missing you the whole time.
Is because you weren't running garbage collections that way, the memory itself still going up slightly?
Yes, yeah, the graph itself, we weren't forcing garbage collection in any
Yeah, we don't
capacity.
actually force it, no.
Yeah, and because the debugger integrated tool, for those of you that are sort of .NET aficionados, works using debugger APIs, not profiling APIs. A profiling API actually walks the heap by forcing a garbage collection, so it would come back down. The debugger walks it not forcing a garbage collection. So, question way back there. Is there any support built in for iDisposable was the question. We don't have any rules built in, so we're not going to directly tell you. But if you run the managed code analysis tool that ships in Visual Studio, the static analysis tool will tell you if you have iDisposable objects that you're not calling dispose on.
Yes.
You use these same tools to compare snapshot core dumps that you take from a running application?
So the question was, can you use these tools to compare snapshot core dumps? So for the managed memory, if you have the enterprise SKU of 2015, you can get the managed memory view from a dump that has the heap. You cannot, and you can actually do that in 2013 as well in the ultimate SKU of Visual Studio 2015. You cannot get access to the native memory information because that's working on an allocation tracking basis. So when we have a dump, obviously we have no history of tracking allocations or deallocations. Yeah, so when you have a dump file, if you stop by the booth tomorrow, I'll be at the booth, I think, around 10:30 a.m. Up on the 3rd floor, and I can walk you through how to do that. But you can pick a dump that's a baseline of a previous dump.
Yep.
All right, so we're going to go ahead and move on.
Get more questions at the end.
And we'll be up here at the end, and as I mentioned, Angelos and I will both be at the booth upstairs on the 3rd floor at various points tomorrow as well for Visual Studio. So we have basically same application here that Angelos was running before, and we're going to go ahead and launch it. And I've been working on some new features.
This is one of them.
Oh, got
Stop
it.
debugging. Start it again.
Actually, I can explain what that was later, but that's OK. It was the debugger warning me that I was launching an optimized build of the process, and that I had just my code on, which meant that I wasn't going to see anything useful.
Using a very scary dialogue to do that.
So if you notice here, Angelos, it looked like it took a little bit longer to start up than I really wanted it to. So let me go ahead and launch that again. And it kind of just sits here and spins like our initial demo. So I want to figure out what's going on. And I could have used perf tips to walk through it like Angelos did, and it turns out that there's actually nothing in my code startup path. Angelos fixed that piece of the puzzle. So what do I do now? I'm going to drop down here to this menu that says Start Diagnostic Tools without Debugging. Has anybody seen this page before in previous versions of Visual Studio? It was introduced in Visual Studio 2013. Okay, about a couple people have seen it, not many. So this is the one-stop shop for all of your performance tools that we haven't been able to bring into the debugger yet, or may not make sense to bring into the debugger. We have a CPU usage tool, and by default, I'm only seeing tools that apply to the application type that I'm debugging. So if I click the Show All Tools, down here I can see tools that don't apply. So there's an energy consumption profiler. This is only for the Windows Store apps. An HTML UI responsiveness profiler. Obviously, that only works with HTML apps. And a JavaScript memory profiler. Obviously, also works with JavaScript apps. So we don't show those to you by default. You don't have to make decisions about like, oh, this looks cool, and then you get annoyed later when it tells you it didn't work. So we have CPU usage. We'll look at that. Somebody asked about GPU usage. So while we don't have it in the debugger directly, there is a GPU usage profiler in Visual Studio if you need to look at, you're doing something that's graphics intensive. This memory usage tool is something that was built in Visual Studio 2013. Effectively, what Angelos just showed you in the debugger, we consider to be, they're about functionally equivalent. So assuming you want to work with the debugger, that's what we would recommend using. But if you want to use something outside the context of a debugger, this is available to you. A network tool, this is a new tool. It's actually a bug. This is the RC that it's showing up for this application type. At the moment, it only works for Windows Store apps, and that will be true in Visual Studio 2015, RTM. But it is very much, we've heard the feedback that people would like that to work for other types of applications as well. So I promise it's on the radar. The performance wizard, we'll talk about that a little bit later in the demo. And then a timeline tool is a tool that works for WPF and Windows Store XAML applications. So I'm going to go ahead and launch that, and notice that I can combine these tools because they're compatible. Tools that are not compatible with them gray out. And I'm going to click Start, and I'm going to profile what's going on in the startup path of my application. You can see that I have a live graph drawing here. Well, this is unresponsive, so that was annoying, but I can see my CPU usage. And so let me go ahead and stop, and let's look at the report that's generated. See what's going on.
So one big difference there is that you have to actually stop the apapplication.
I do have to stop the application now, that's correct, yeah. And wow, at the top, I can see this big, scary set of graphs. So that's another little trick in Visual Studio. If you ever want to really drill into something, we have a full screen mode, and so it gets rid of pretty much everything else. And so at the top, I'm presented with some swim lanes. The first swim lane, this is coming from the timeline tool, and this is going to show me the UI thread utilization broken down by how WPF effectively understands my UI. So I can see where I'm doing parsing, where I'm doing layout, where I'm doing rendering, I/O, executing application code, and there's other random stuff in the framework happening. And here I can see I'm pretty much pegging the CPU on the UI thread, and if it wasn't responsive, I couldn't even drag it out of the way, with my layout and rendering code. So how do I figure out what's going on there? Well, if I look down here, I can see that I basically had no frame rate going on there either. So I have a frame rate graph, and that makes sense because, well, if I peg the CPU on the UI thread, I'm not going to get any frame rate. Nope. And then the CPU utilization, as you pointed out before, this is a quad-core machine. So even though my UI thread's pegged at 100%, it's only showing me that about 13% of all my processors were being used. So I'm going to go down here, down to the bottom half of the table, and you'll see two tabs. I have the timeline tab. I turn that tool on, and we'll drill into that. And then I have a CPU usage tab, and that's going to show me the results of my CPU profiler as well. So I'm going to look down here, and I'm going to find my layout where I'm spending all the time. And I can see that I'm laying out about almost 2,000 objects. That seems awfully odd for that relatively simple application.
It's a small screen, right?
Yeah, there's not that much stuff on the screen. So I'm going to go ahead, I'm going to drill in, And I'm going to drill down in here and start looking at my content presenter. And this is showing me everything that's being drawn in my WPF. Again, this works for Windows Store applications as well. And I can see that the scroll content presenter is drawing down here. It's drawing a lot of items. This group item is drawing 1100. And then a stack panel. So, I got it. OK, I see this group item thing. I know what's wrong, Angelos. I'm going to go fix it.
Why? What happened? What did that tell you?
Oh, OK. So actually, we've gotten bit by this many, many times in Visual Studio as well. So this really happens to people all the time. Turns out in all of the XAML frameworks, when you enable grouping in a data-bound list, the list actually won't virtualize itself, meaning that it's going to go through and it's going to draw every item in the list, even though only a couple of them fit on the screen.
That's why you had 1200.
That's why I'm drawing 1200 things, right? Because I'm not virtualizing my list of pictures. So I'm going to go ahead and fix that. And like any good performance demo, I can fix it by changing a Boolean. But just to make sure I really fixed it, let's go ahead and run the tools again. Build, measure, learn, right? Make sure it remembers the last thing that I selected. Start. It's going to come up. It seemed a little faster, but it's still not what I'd want it to be. So maybe my Boolean wasn't quite as foolproof as I thought it was.
Yeah, because my version came up a lot faster than that.
I'm
just saying.
Fair enough. And I can see that I pretty much got rid of all the rendering time. There's very little rendering, and the other one stays up, so I can go compare them if I want. But I have not eliminated any of the layout time. So it looks like I'm still laying everything out. And this really happened to me. I thought I had actually fixed a bug one time with virtualization. And it turns out that if I go drill down through here, I'm going to see that I still am actually laying it out.
Yeah.
It's just not doing the work to actually draw it. So it won't be rendered until it scrolls into view, but it's still going to be drawn. And
It still does all the calculations, it looks like.
And it's because in WPF, by having simply a group style defined, even though I haven't actually grouped the content that's been data bound to it, I actually am still rendering everything, or laying everything out, even though I'm not rendering it. So that's something that would be easy to miss if you didn't go back and run the tools again after you thought you fixed an issue. So that kind of illustrates the reason to go run tools again and make sure that you fix things when you really think that you did, as opposed to taking a guess, changing some code, and just moving on. So let's go ahead and launch it one more time, just to make sure that I'm really happy with it. And boom, that comes up pretty much instantly. If I were to run the tools again, you'd see that I'm taking about 400 milliseconds to render that whole page, as opposed to many, many seconds. So anything else that, any questions on those particular tools? So just a brief review. We briefly went through the diagnostics tools without debugging page, and we talked about the timeline tool that is new to 2015.
There were a couple of questions, I think.
Looks like what, sorry? Concurrency visualizer? Okay, so the question was, this looks like Concurrency Visualizer, which was a tool that used to ship in Visual Studio and now ships on the gallery. No, this is not the Concurrency Visualizer. Concurrency Visualizer is still shipping on the Visual Studio gallery as a separate installation to Visual Studio. Do we have support for multiple threads? The tool that I just looked at, and we'll dive into the CPU tool, focuses mainly on the events that are occurring in the XAML runtime, so WPF or the Windows Store app XAML ones. The CPU one will give you a view of what's going on in all the threads, and we'll talk about that one next.
Just one more there.
Yes? So the question was, do you need PDB files in analyzing? We don't need PDB files to build most of the view that you see here. The CPU tool, which we'll look at in a minute, will need PDB files to be able to give you your function names. So that's a good question. Ted, why don't you come talk to me afterwards and we can dig into that? And I'll try to mention the symbol files when I do the CPU tool next as well. So for the sake of time, I think I'm going to move on because we're running short on time. And we're going to go ahead and dig into what the CPU profiler looks like now. So you saw me mention it before, how we turn it on. So now that I have this particular application running, I'm going to go ahead and just launch it under the tool, under the diagnostics, under the same tools that I was running before. And when I start profiling, I'm going to pretty happy with how it loads, but I notice as I scroll, it's actually really, really slow to keep up with my scrolling. And so that's not really what I'd ideally like. And so I'm going to go ahead and stop collection. I can see I'm pegging the CPU again, pretty much on the UI thread.
Well, this is something
there.
really hard to debug with perf tips, right?
Yeah,
The
this is something
scrolling
I
is
cannot
not
debug
kind
this
of
with perf tips at all. And so I can see all of my scrolls here. There's these little spikes in the layout. And so I can see that I'm rendering or laying out a lot of stuff whenever I scroll. And if I go drill in here, I'm not going to be able to, I'm going to see I'm laying out items as I scroll, so that makes sense. So why is it being so slow? I'm going to flip over to the CPU usage tab, and the CPU usage tab, by default, it's going to show me a couple things. It's going to show me a call stack. These are the code that was executing, how the tool works. It takes a call stack sample once every millisecond, and then it builds an aggregate report. And I can see that 85% of my time was being spent up here in main, and then there's this external code on the stack. This is a bunch of framework code. By default, we filter that out for you. And in case you want to know why we filter that out for you, this is what it looks like when you don't have that. And so let's go find my, I think I saw my code under there that was like get image, and it is buried this many. So you were asking about symbol files. If I had symbol files for the framework code itself, I am now in a, so if I had symbol files where I have like clr.dll and mscore.e.dll, it would be showing me the function names that we're executing. Because I don't have symbol files, all it knows is that it was executing in the module. So that's where symbol files are required to be able to give you specific function names that are executing. So let's go ahead and turn this back on. And I'm going to go ahead and filter this back out. And so CPU sampling here, even though the problem's not in my code, I can get a really good clue as to what the problem is based on my code that's being called. And I can see that this get image is being called. And I know that as I'm scrolling, that's a data-bound list, so it's retrieving the image file.
But I thought that you fixed virtualization.
I did fix virtualization. So it turns out as I'm scrolling, what's happening is that data-bound control, it's rendering the image on the UI thread. So it's trying to, as I scroll, as every item comes into view, it's trying to retrieve it, and then it's trying to render it, and it may have scrolled out of view.
So it draws it and then it throws it away.
It draws it and then it throws it away, right?
Okay.
So I could think about potentially being a little bit more efficient about this. And this one really, I really can fix with a Boolean, I promise. And I'm going to delay load the images to, I've implemented some functionality in my application so that when I scroll, it's not going to actually load the image until I detect that the user stops scrolling. So as I scroll, you'll see this be a little placeholder, and then it's going to go retrieve the images and do the work to render those on the UI thread.
All right. Now this is better than mine, sure. Okay, fine.
So great. So we fixed that. The other thing I will mention on the CPU tool, has anybody here used the CPU profiler in Visual Studio before? Okay, about a third of the room. So if I click this Create Detailed Report button, it's going to go open and it's going to bring me into a much more detailed report view. This is probably what you're used to with CPU sampling in Visual Studio before. So we tried to move the tool, or in the process of moving the tool, into this what we call the Diagnostics Hub, or Performance and Diagnostics Hub, where you can run it in conjunction with other tools, like the UI tool or the network tool or some of the other tools. But we realized that there's sometimes that you just need a much richer view on your data. And in that case, we have this detailed view. It has a lot of views. I can view the call tree, which is what we were looking at before, but I can see CPU breakdown by modules. I can see CPU breakdown actually down to the function level if I want. If you want to get really brave, you can break it down to the individual line of code for modules that you have PDBs for, so it can map that back to the code. So that's something to be aware of as well, that functionality is available. And if you need to drill in more than this current view shows you that runs in conjunction with other tools. So any questions on that? All right, so just a brief review. We talked about the CPU tool. It shows me full stacks, both mixed mode, so .NET and C++. Gets all of those. All right, so last demo, we're running short, but this is a tip, because I'm sure some of you are wondering, how do I run tools in production? And so the last quick tip is you can, Visual Studio profiling tools are actually part of the Visual Studio Remote Debugger. So if you just go online and you search for Visual Studio, pick your version, 2015 remote tools. You will find a download page for those, and 15 RC, you have to get the right version. And there we go. And so if you just install the remote tools, this includes the remote debugger as well. The profiler comes with that. And another tip for you is actually if you simply go to the directory on Visual Studio, so it's your Visual Studio root installation directory. I'm sorry, this is kind of small. Magnifier. And then you go to the Team Tools folder. There's a Performance Tools folder. You can actually X-copy this folder over, and if you're on Windows 8.0 or above, CPU sampling will simply work X-copy. So for people that want to go debug in some environment where your admin may not be very happy about you actually installing the remote debugger, CPU sampling, if it's the right version of the OS, is actually usable in via Xcopy. And then all you simply do is you open a command prompt, go to this particular directory, and then you can use, there's documentation depending on your version of the OS, vsperf.exe or vsperfcommand.exe will then let you use those tools. So the last thing I wanted to show is I promised I'd show the what we call the performance wizard, and for those of you who have used the profiling tools before, you'll recognize this, and there's still certain project types that require this, and we have 4 tools in here. So we have CPU sampling, that's what we just looked at, except if you go through this particular path, you'll end up in that detailed report automatically. You don't have the opportunity to run it in conjunction with other tools. There's an instrumentation profiler. The instrumentation profiler records every function call, so we know exactly how many times it was called, exactly how much time was spent in every function. This can be incredibly powerful. It will also generate an awful lot of data and make your application run significantly slower. So be judicious about when you use it. We had somebody that wanted to investigate a performance problem in Visual Studio one time. They were new to the team. They had no idea what the code was. So they just instrumented and ran it. And they had an 8 GB file in like 2 minutes. So use judiciously. .NET memory allocation. This is something that for the most part, you probably want to use the memory tools that we showed you before. This is going to track every allocation. This is probably only interesting to you if you have a really, really critical code path that even Gen 0 garbage collections are going to be a problem for you, and then you want to go use this tool to just optimize that code path. This is not a general purpose, like solve my memory problems tool. That's the one that Angelo showed before. And then lastly, if you're doing a lot of concurrency stuff, we have a resource contention profiler that is going to show you where you're contending on resources, so lock contention. So if you are not getting the throughput that you would expect in a parallel environment, you can run this tool and see that. So those are just a couple quick tips. So we talked about performance profiler. I briefly talked about the standalone profiler. And with that, any questions? All right, well, thank you very much.
There's one over there.
Okay. Yep.
So are all of these performance tools available in basically the licensing question?
So all of the performance tools are available down through the community SKU. So up here we have, I mentioned briefly, and then we'll take a couple more questions because we're almost out of time. I want to respect everybody's time since I know it's late. A link to our blog. So we blog about all the stuff that we do. We do use user voice to prioritize. And when you use Visual Studio, use send a smile or send a frown. I promise somebody reads every single one of those. And please fill out an evaluation.
They do.
Thank you very much.
They do. Thank you.